All right, so as you can see here, I'm going to be talking about the neuron, the axon, and how a signal or an action potential travels on the axon. But first off, I'm just going to talk about an action potential itself and how it forms. All right, so resting member potential down here is around -70. When a neurotransmitter binds up to these dendrites up here, they have an effect on the neuron known as depolarization. This means they make the membrane potential less polarized or cause it to move closer to zero. This depolarization will cause the neuron to reach its threshold membrane potential. This is generally around -55. When threshold is reached, a large number of sodium channels open over here, allowing positively charged sodium channels ions into the cell. This will cause massive depolarization as membrane potential reaches zero and then becomes positive up to this +40. This is known as the rising phase of the action potential. The influx of positive ions creates the electrical signal known as the action potential, which then travels down the neuron and the axon of the neuron. Eventually, the action potential reaches its peak. Sodium channels close up here. Potassium channels open, which allows potassium to flow out of the cell. This loss of potassium promotes repolarization, which is this phase right here, which is also known as the falling phase of the action potential. The neuron returns to its resting potential right here, but actually overshoots it right down here and becomes hyperpolarized over down here. During this phase, known as the refractory period, it is very difficult to cause the neuron to fire again. Eventually, the potassium channels close, and the membrane potential returns up to the resting potential ready to be activated again. The signal generated by the action potential travels down the axon of the neuron and it can cause the release of neurotransmitters down here at the terminal end. All right, so let's talk about, let's do an example of you got stabbed in the hand. So basically at the dendrites over here, they'll be stimulated by the sensory output of being stabbed. The dendrites will then allow positive sodium ions to flow into the neuron from the outside and the positive potassium ions to flow out through these chemically gated sodium channels and potassium channels. This is due to the neuron being more negative on the outside than it is on the inside. This will depolarize the soma, pushing it past its threshold of that -55 I talked about earlier, triggering action potential at the axon hillock, which will then fire the neuron. The action potential will travel down the axon through this thing called electrotonic spread. And the axon has low resistance, and these things right here, the myelin sheath, I'll get to those in a second, but those have high resistance and they're an insulator. So the myelin sheath keeps the potential from leaking across the axon into the space outside the axon as it passively travels down the axon through this electrotonic spread. If there was no myelin sheath here, then the current would dissipate across the axon, causing it to go slower and slower. Myelin sheath doesn't cover the whole axon, as you can see, it's in these little areas. This is because it is covered. This is because if it covered the whole axon, then the signal at the terminal end would be really weak over here. It wouldn't be able to trigger other neurons. Instead, the myelin sheaths are separated by these things called nodes of Ranvier. These gaps have high voltage gated channels up here and down here that release action potentials to help boost the signal to help keep it strong. The myelin sheath will keep the action potentials going fast through here and have minimal energy loss, and the nodes of Ranvier will boost the signal to keep it going down the long axon. This whole type of conduction is called saltatory conduction.